Good morning. I'm Mark Sneer, the chair of the Cray and Ferbach Awards, and it will be my pleasure to introduce this morning the talks of the two winners of the Cray Award and of the Fernbach Award. But before we listen to them, we shall have a small surprise. It turns out that Bill Camp family did not make it yesterday, so we shall do a repetition, a déjà vu. We shall present to him again the award for the Cray Award. For those that don't know Bill Camp, he has been a Sandian for decades, I think 30 years or so. He is responsible for Sandia being a powerhouse in high-performance computing. He is responsible for the Redstone that was a major turn for high-performance computing and a major turn, I think, and a new start for Cray. And I think he bears no little responsibility for Intel being, again, a major player in high-performance computing. So it's my pleasure to have Bill Camp here, and I also invite Tom Compte, the previous chair of the IEEE Computer Society, who is going to present the award.
Thank you, Mark.
Thank you.
So before I start, I would very much like to dedicate this talk to three people who have had an enormous effect on my career. Obviously, Seymour. I actually grew up on his machines. What I know about balance, I learned a lot. My first machine was a CDC, and I went through the Cray machines with him, and I had the unfortunate duty of telling him we were going to cancel a C90 we had planned to buy, mainly because it was too good a computer, and I knew that Sandia would never move to MPP if we had a C90. Ed Barsas was my first boss in computing at Sandia. He wasn't a computer scientist or computer engineer, but he was a great strategic thinker. And he was the person who managed to talk Don Austin at DOE into giving us the money to buy the first large N-Cube-10, a 1024 processor system, which of course, in my opinion, began much of the MPP revolution. Gustafson, Montry, and Benner won the first Gordon Bell Prize based on that machine. And I've appreciated over the years how much leadership Ed provided to the laboratory. And of course, Bill Blake. I'm sure Bill was a friend of many of us. It was a great shock to me. He and I have been friends, colleagues, co-workers for years and years, and I will truly miss that person. So I'd like to dedicate this to those folks. And I'd also like, the Red Storm team was so large that I'm pretty sure that a great deal of this audience right now is composed of the people who made Red Storm possible, both at Sandia and at Cray. And I'm not going to read the names of all these people. You know who you are. There are literally a couple of hundred people who worked on this very hard. Three people stand out that I can't go without mentioning. Jim Tompkins, my partner in crime on Red Storm. Jim Sundit, one of the greatest engineers that I've ever known in terms of putting things together. And Pete Ungaro at Cray, who just wouldn't let go of this partnership even when it looked like we were going to kill each other. So it was, and of course, before Pete, well, I don't want to go into that, Burton. Well, I would just like to thank those folks because really it's our prize, it's not my prize. So I want to talk about three things, and I may not get to all three because I have to get this done in 25 minutes. I want to talk a little bit about why supercomputing is important. I want to reminisce a little bit about the Red Storm process and just say a few words about where supercomputing is going, in my opinion. So for decades now, the principal purpose of supercomputing, any form of computing, really has been insight. And it's going to continue to be insight for quite a while. And I'll talk a little bit about climate, not much at all, a couple of words actually, but obviously one of the really big societal problems that we have to deal with today is what to do about climate. And I would submit the first thing we need to do is make sure we know what we're talking about. And the climate codes that we have today have the possibility of becoming predictive, but right now they're really insight codes, and we need to really increase supercomputing power to make that happen. Some of the really emerging areas that I think are going to be very important in the years to come, microeconomics. I believe that you can use microeconomics to actually make macroeconomic forecasts using things like neural networks and Monte Carlo methods and training these things with real sociologists at hand. Obviously, intelligence and counterintelligence has always been a real issue both for industry and for government, and it's only going to get bigger with the kind of data we're dealing with now. Game theoretic analyses, well, that's a little bit of what I was talking about with microeconomics, the big graph and a lot of other things. But there are some other things that aren't really insight, but actually getting something done. For years now, 25 years ago, I think I started something called Materials by Design for the DOE that was a multi-lab effort. And we got a lot of money and we had a lot of fun, but we never actually discovered a new material because it's a hard problem. It's hard to do the forward problem. It's really hard to do the inverse problem. The other thing is, we have a lot of projects around the world today looking into how do we build a human brain. And I think we're doing it right. First, we're trying to simulate what a human brain is in the digital world. Eventually, we'll build a human brain using analog computing, but we won't get much insight when we do that. We get the insight from what we're doing now. And with apologies to my friend Steve Wallach, the real issue to me is how do we create the soul of a new machine? And I mean that metaphysically, not metaphorically as Steve did. It really, what is consciousness? What is self-awareness? And when are we going to create a machine which is self-conscious and self-aware? I'm not sure we have a clue what the algorithms are, frankly. So one of the things that we should do a reality check on is, and a lot of people don't realize this, including many of my managers when I was at Sandia, just because you make a computer twice as big doesn't mean that the answers you get out of that computer are twice as accurate. Almost all the problems we want to solve are not linear. They're in P or in NP. The really interesting ones are in NP. But even in P, the speed up or the problem accuracy actually goes as some root of the size or the expense of the machine or the speed of the machine. And typically, for example, for climate, it's probably the cube root. For fusion, it's probably the fourth root. Well, those will look a lot like a logarithm, so you're not really getting as much speed up as you might hope as you make the machines bigger and bigger. And that's why you hear people talking about exascale and yotta-scale and who God knows what other scale out there. But in part, it's because things don't speed up as quickly as we'd like. Now, I'm going to make a bold statement, which I think some people would disagree with. I don't think exascale gets us there for climate modeling. And the reason is simple. We need to resolve clouds. We need to resolve cloud physics. We need to really increase the mesh discretization capability in these machines. And when you go through that, we need machines that are about a factor of 10 to the 8th faster than what we have now. And that says something more like yotta-scale than exascale if you want to really do the climate problem. Now, talk a little bit about brains and neural networks, and I'm misquoting my friend Descartes here. In 1998, Jerry Jonas, the former CTO of the CIA and my boss then, actually one of the geniuses of the SDI initiative, said, well, we have this big computer camp, it's called RED. And I just noticed it's got as much memory as a brain. So are we there yet for simulating a brain? So I went away for a couple of hours and misused my notions that I had brought over from my early days in analog computing of what it would take to simulate brains, and I gave him a time scale, and I basically said about 2030 will be bird brains. I called it Camp's chicken brain chart. And if you look at this, we're talking zeta-ops, really, to simulate in great accuracy a human brain, and we're talking 2040 and beyond. Now, I know there are people in the room who are working hard on these kinds of projects and might disagree with my details, but in principle, you've got to know this is an exponentially growing problem to do this. And we need to do it because if we were to build a brain out of analog computational parts, it's like doing quantum computing. You really don't get that much insight. You might have something that works or doesn't work, but finding out why with analog parts is not nearly as easy as it is if you can scan the data all the way through it the way you can in a digital simulation. So the last thing I want to say about why supercomputing is an overarching concern. And the concern is that flagships drive fleets and fleets drive hegemonies. And what do I mean by that? Anybody recognize this? I'm sure some people do. Take a look at it. You recognize this? Maybe this will help. Nobody does, I can see. This is Waxahachie, Texas, folks. The first slide was CERN outside of Geneva. The second slide was a picture of what the superconducting super collider in Texas was going to look like. And the third is a tunnel from that. And as most of you know, there's an abandoned tunnel under Waxahachie now that was going to be twice as powerful as the CERN collider is. Why is that important? Well, choices have consequences. After World War II, America was the last country standing, and basically we inherited a lot of talent from Europe and elsewhere, and we had a lot of native talent, and we became the dominant power in experimental nuclear physics, especially high energy physics. And we were just continuing along that path, and somebody said, let's go do something that goes beyond what Fermilab's doing. And so we decided to build this super collider. Well, unfortunately, we overran the budget, and people, very brilliant people, Nobel Prize winners like Phil Anderson, really opposed it because he thought it was stealing money from the small physics that needed to be done. I submit he was wrong, and that it really had consequences, because today, CERN is an awesome facility, and the center of gravity of nuclear physics has moved firmly from the United States into Europe, and it's likely to stay there for the indefinite future. So what's that mean? Well, supercomputers are flagships. They're gigantic capital investments that only last 5 years if you're lucky. And we have to constantly go back and convince our managers and our funding partners, either in industry or in governments, to fund these things. It's a never-ending story. But if we were to stop doing it, I think we'd be sorry. I submit that Sandia National Laboratories is one of the premier computational science research facilities in the world. And I would also submit that the fact that Sandia has repeatedly been at the top of the 500 list with supercomputers has attracted that kind of talent and has helped to keep them. And I believe it's possible to have that kind of talent without having a flagship to pull them in, but it's not that easy. And I think that we need to keep it in mind that supercomputers are important for more than just the speed at which you can solve a single problem. Now, I want to turn to my second topic, which is a few reminiscences about Red Storm, the reason, in fact, I'm here today in large part. This may be the most successful family of supercomputers ever built. In 2004, XT3 came along. We called it Red Storm as our code name. 2005, simply by a frequency upgrade, that became the XT4. 2006, XT5 became a multiprocessor node, same network, same infrastructure. 2009, the XT5 became the XT6. 2010, we finally got rid of the C-star interconnect in Red Storm and replaced it with Gemini, but it was basically the same infrastructure. And finally, in 2012, the XC30 came along and completely changed the game with the new Aries interconnect and a whole bunch of other good stuff, and it was the end of the Red Storm era. But over nearly a decade, that machine was at or near the top of the supercomputers in the world, and many institutions had it. And it's unusual for an architecture to last that long, and I think it has to do with the fact that we did a very good job at the beginning in designing this. And I'll tell you a little bit of the history, and it's obviously very idiosyncratic, and there are people who say I got it wrong, but in 2000, Jim Tompkins and I decided that we needed to create a follow-on to ASCII Red, which was an Intel machine that had been very successful, the first teraflop machine in the world, although some of the folks in the T3E world might disagree with that, but it was either that or the T3E. So we had no money, we had no facility that would hold it, and DOE actually was struggling for money at that time, and so how are we going to do it? Well, there are a few other things that made this a minor miracle. SGI had sold Cray Research to the small company, the genius behind it sitting there front and center, Burton Smith, a little company called Terra. Digital had been acquired by Compaq. That wasn't a problem really, but then Compaq was acquired by HP. Originally, Jim and I had been talking with Bill Blake and the folks at DEC and Compaq about what we would do to build a scalable EV7. EV7 was the last of the alpha architecture, a wonderful processor. We were going to build a machine based on that. Well, as it turned out, HP did not share the same interest in doing this kind of high-end project that Digital and Compaq had. Paul Messina was the director at ASCII then, and we had actually gone to him with a project we called Red Skunk. Red Skunk was intended to upgrade ASCII Red, and it was very clever, and it was going to put EV7s in it. It was really going to be a nice machine. And Paul said, this is wonderful, but really it's a dead end. You should spend your time thinking about something new instead of doing this. So go away and come back when you have something new. In the meantime, Tom Hunter became the lab director at Sandia, and he threw his support behind doing this kind of thing. Bill Reed had replaced Paul Messina at NNSA, leading the ASC program, and he actually approved letting us come out with RFIs, requests for information, and ultimately requests for quotes for a new flagship system. We got a lot of answers to that RFI, but unfortunately none of them met what we thought were our criteria. We deemed none of them responsive. So we said, okay, we're going to do something different. We're going to use our design, and we're going to issue an RFQ to see if anybody is interested in building Red Storm to our specs. Only 2 people responded, HP and Terra/Cray. Only the Cray response was affordable. HP's response was about a factor of 2 too high for us. So we were down to 1 vendor. That was okay. Well, we got a vendor. That's good, a partner. Unfortunately, my CFO took a look at this and said, you can't do this contract. The contract is worth more than the company you're trying to do it with. And I said, no, you're wrong. This is a good company. They can do it. I will write such an ironclad contract, and Burton knows I did. Jim Tompkins actually did, to tell you the truth, that we can manage this. And furthermore, we're going to create a tight partnership between government and industry like you have not seen before to do this. And we're going to do it in under 2 years. We said we can do this in 23 months. Now, I've worked at Cray and I've worked at Intel, and I can tell you nothing gets done in 23 months. And we didn't do it in 23 months. We did it in about 27 months. But I think that to create this kind of architecture in a little over 2 years is nearly miraculous. And it worked. So in a little over, not only that, but we found a way in 1 year to build a new computer building that was big enough for Red Storm. It was actually first class and only cost us $5 million, and we got it done in less than a year. So I'm as proud of building that computer building as I am in some ways of the Red Storm project, because other DOE computer buildings were measured in numbers that were 8 or 9 figures of dollars to build them. And it was really a partnership. In all likelihood, Cray couldn't have done it alone, and I know we could not have done it alone. So how did we do it? Well, the first thing is we left some really good stuff out. We left out something that I fought for that Jim Tompkins didn't like that well, which is a global address space and the ability to not have to do messages to use the machine. Didn't hurt scientific programming too much, but it really hurt everything else that you'd want to do with a supercomputer. I said, we'll come back and get that later. It would be good to have. George Cotter wasn't happy, but we're not going to do it. Because if we had done it, we would not have gotten the machine built in the time frame we wanted to build it and at the cost we wanted to build it. Nearly everything in that machine was high volume commodity and pre-existing software, except for specialized things that we did for the project. It only had one truly custom part, the C-Star network interface and router. That is the network that moves data around the machine so that these processors can work together in a collaborative fashion. The other thing we did was Steve Scott had a project, I believe, with the US government. Steve was at Cray, and he had developed a new system called Black Widow. And he had a router core that looked to us like, well, gee, we don't have to design a router, we're just gonna use Steve's. We could not have done that if we had worked with HP, because Steve was at Cray, so that was God smiling on us in some way that we were able to use Steve's router. And then the thing that really made it for us, and later got me a job at Intel actually, was that we used AMD. Intel had proprietary interfaces and was reluctant at that point to produce a Xeon-like 64-bit architecture ahead of when they wanted to come out with it. Well, it turned out that AMD had just come out with this code-named Sledgehammer architecture, which was the Opteron today. And what was important about it, besides that it looked like it was a cheaper knockoff of an Alpha type system in some ways, but what was really important was, it had this thing called hypertransport. Hypertransport was a very high-speed interface that was open. You could program to this interface no matter who you were, as long as you wanted to buy Opteron parts. That, as much as anything else, Steve's router and that hypertransport interface enabled us to go ahead and do this project. So this is something that Cray stole from me, and I stole it back from a presentation that Bill Blake gave not too long before he died. And it shows what our architecture looks like. And essentially, the thing to get out of this is that this is a partitioned architecture. It's a keep it simple, stupid approach to computing. The only complex things are the things humans need to interact with. That's the service and I/O nodes, maybe the visualization nodes, those kinds of things. The compute nodes all run extremely simple software that essentially starts the job up, lets the job run, and when the job completes, cleans up after it, and the applications own a share of that computer while it's running. That has been our mantra from the days of the N-Cube all the way through Red Storm, and Cray has managed subsequently to turn a version of Linux into something that runs essentially as lightweight as that. But at the time, we thought we had no choice but use one of our lightweight kernels for the operating system. So it's a true MPP, it's distributed memory, it's fully connected 3D mesh interconnect, had a large number of nodes, it was over 100 cabinets. We did something called red-black switching, and the way to think of that is we found a way that you could hook this up to a whole bunch. We started initially with 2, but in principle, quite a few networks that didn't trust each other, couldn't share data with each other, and really had to be isolated. But we couldn't afford to buy a large number of machines. We couldn't even afford to buy 2. So we simply had a classified end of this machine and an open end of the machine. And you either had your end plus the whole middle of the machine, or you just had your end. And that has worked very well, actually, for Sandia over the years. I don't know that anybody else has adopted it, but because of some of the unique things we did. And it's not critical to the architecture, but it was a nice add-on to it. So as I said, we used functional hardware partitioning and functional software partitioning. One of the big arguments between us and Cray, which we lost, was table-based routing instead of source-based routing, and it turned out it worked fine. Took a while to prove, in fact, that we were deadlock-free. Thank you to Sandia for doing that. It was a nice job. But it worked very well, and I believe that routing, table-based routing for the time being has won that argument. It had less than 2 megawatts total power. Think about where we're going with exascale. We were down to 2. That was actually good for the time, and it only took about 3,000 square feet to build it. So the most important thing about Red Storm was balance. In my opinion, and it took me a long while to learn this, balance is what makes supercomputers work on real-world problems. So some of the things that we didn't do, and I don't want to start an argument, but I still am not convinced that large cache-coherent memory spaces help scalability. I think they actually hinder it. I think programming that is not aware of locality doesn't mean that it has to all be local, but you should be aware of how to use locality in a way that improves the performance of your code. Virtual memory, to me, is not really a plus for scalability. Non-contiguous memory makes life a little harder for you. It's not that you can't do it, but it's better to have contiguous memory. And probably the worst thing is global locks and synchronization, especially heavyweight global locks. The only way I know of to make a large memory space, global memory space work, is to have a very lightweight synchronization and barrier mechanism that's essentially local and can be set quickly and unset quickly. And Cray has done this in the past. Burton has thought a lot about it. I know it can be done, and that, in fact, the T3 is a living example that you can do that kind of thing. So I won't talk about resilience except to say you could build this architecture, and by the way, a beautiful architecture in some ways was the Intel Paragon. Unlike Intel Red or T-flops, which was an incredibly reliable machine, the Paragon was a beautiful machine, but it was not reliable. And that's because not enough system look at the resiliency issue took place before the Paragon hit the floor and got in the marketplace. I don't think I want to talk too much about resiliency. I do want to mention why it was so easy to do Red Storm. We had a lot of examples of how to build a good computer. The N-Cube 10, the N-Cube 2, the T3D and T3E, both of which I was involved with when I was at Cray, and it was a wonderful experience. And of course, the Intel T-flops. On all of these things, the critical thing was the balance factor. How are we doing? Good, we're fine. Give me a minute and I'll finish up here. So I just tell you that balance is incredibly important. The real speed, in fact, can be shown to depend more on balance than it does on processor speed. So, Sic transit gloria mundi. For those of you at the Catholic school, you might find this amusing. Sandia's ASCII Red in 1997, fastest machine in the world, cost us $67 million, took almost a megawatt. Red Storm, 2005, 40 teraflops, over a megawatt, cost us $90 million. Both those machines, well, already ASCII Red performance can be found on a Sony PlayStation. The prediction of Cray is that by the time we get to 2019, NVIDIA-based PlayStations will in fact be faster than Red Storm. And I was going to talk a little bit about the future, but I found that I didn't get there. So I will stop with my reminiscence of Red Storm, and thank you very much for your attention. And I need to give this.
Thank you, Bill. We have time, I think, for 1 or 2 questions, but no more. So if somebody has an urgent need for clarification. And I think one more thing you could say, those that don't learn from history are condemned to live it again.
Yes, absolutely.
So thanks for your talk about the history. I think there are many messages that we could take for the future. So I think we shall skip straight to the next speaker. So let's thank again Bill. Thank you.